Okay, thank you, Davide, for the introduction. Thank you, organizers, for the invitation. It's really nice to be here and share a little bit what I know about experimental overview on time result spectroscopy. And here is the outline of my presentation. I will start with some general basics on time result spectroscopy, particularly defining the so-called pump probe principle, the time scales that one can address with this technique, and some experimental requirements for performing a time result spectroscopic measurement. In the second part of my talk, I will discuss the three main approaches of this technique, which are basically addressing the non-equilibrium physics of a system after the interaction with photon. And the second one is like the excitation or the probing of bosonic modes and collective excitation. And eventually the goal of achieving optical control of matter phases, eventually addressing non-thermal states which cannot be really addressed by any thermodynamical pathway. And just towards the end, I will flash a few perspectives in the use of time result spectroscopy. And because I will touch kind of different parts and also referring to different works, feel free to interrupt and ask questions also during the talk. Just a few remarks on these two approaches that I will discuss. The non-equilibrium spectroscopy will be kind of analyzing more detail, presenting you this particular work with time result photoemission spectroscopy on a system which is supposed to be an excitonic insulator, and we will look particularly at the exciton dynamics induced by a pump pulse. And for the second part, the excitation and probing of collective excitation, I will focus on other recent work that we did together with Davide and Alejandro, where we use coherent optical photon spectroscopy to investigate exciton dynamics in a layer semiconductor. Okay, so let's start with what we probably all know being the basic principle of doing spectroscopy in a steady state fashion. So the basic idea, we have heard already the example of photoemission from on Tuesday, is that when you do a steady state spectroscopy measurement, you have one light matter interaction where the impinging light induces a weak perturbation in the system. And this perturbation evolves rapidly into a stationary state, on a timescale which is much, much faster than the observation time. So as such, in a steady state spectroscopy measurement, what you typically monitor is a quasi-equilibrium state, which hopefully resemble the actual equilibrium of your material. Now, if you want to address dynamics, you have to kind of sample the evolution of the system with a sampling rate which is comparable to the relevant dynamics. However, those dynamics are typically way too fast for any state-of-art device. And this is the situation where the so-called pump probe strategy comes to kind of rescue our measurement. So in a time result pump probe measurement, the idea is that you have two light matter interactions. The first one acted by a pump pulse, which comes on the sample and induce a perturbation on a very fast time scale. And then the second pulse, which is a much weaker one, arrives at a certain delay between from the pump pulse and monitor basically the evolution of the system. And you have to consider this time delay between the two is on the time scale of your interested dynamics. So the idea that the probe is in charge of really monitoring in real time the motion of the system after the interaction with the first light flash. Okay, but in this kind of stroboscopic effect, how fast should we go? What is shown here in this review is basically an overview of the relaxation processes following the interaction between the matter and photons. So starting from the absorption of a photon, you have very fast processes which span on the order of few femtosecond up to a few tenths of femtosecond, and involving mostly scattering among carriers and the lattice. And then later processes can take place up to the microsecond regime. So all those dynamics are way too fast for any device. And on the other hand, you can see from those arrows, we have now sources spanning also like different energy ranges, which can address or be comparable to those timescales. So like we would like to ideally have like pulses with some energy tunability being in the sub-picosecond regime. Now, another important aspect when you do spectroscopic measurements in solid states is that the idea of like relaxation processes, which always involve like energy exchange, is that the exchange is faster if the coupling between the different subsystems you can consider like dividing your material is stronger. So typically a solid state system can be like seen as a like combination of charges, lattice, and spin degrees of freedoms. And if those are coupled, like they can exchange energy. And here I'm overviewing basically the time scale and the energy scale of the interaction processes among those sublattices. I guess in the audience we are mostly like interested in charge and like carrier dynamics, and for those, for instance, the idea that you might want to perturb with your pump pulse this like carrier subsystem, and this is kind of the time scale and the energy scale you need for your light pulses, and then depending on what you want to probe, you need to kind of tune your source accordingly to the scheme. Why couplings are important, like not only because they determine the time scale of your dynamics, but they also really matter at equilibrium. And this is like one pioneer work where like by means of time resolved ARPES, like by time resolved angular resolved photoemission spectroscopy, they were trying to do some kind of time and energy classification of complex matter phases. Like you see here, this was just a graphical abstract, like Mott insulator, excitonic insulator, Pyre insulator are all insulating matter, matter phases, where one specific coupling is the dominant one, being electron-electron on-site Coulomb like interaction, electron-hole attraction, or eventually like coupling between electrons and some lattice instabilities. And the idea is that if you can like follow the dynamics of the system in time and energy domains following a perturbation, you can see from the like relative time scales of the relaxation dynamics, which is the dominant coupling, which kind of act as like the kind of the how to say, like the coupling which determine eventually the phase of the matter. So the idea of coupling disentanglement on the time and energy domain is also one of the typical approach for performing time resolved measurements in coupled system or correlated system particularly. Okay, so I said we want to have time and energy tunability. What I'm summarizing here is basically some of the processes that are typically used to generate ultra short pulses. I mean, the first sub-picosecond laser pulse was exploited in 1999 by Zivile, who got a Nobel Prize for like following a chemical reaction in time by means of sub-picosecond pulses. And after that, like basically the pump probe scheme got a great development, and together with this also development of ultra-short laser sources. And like if you wanna, for instance, stay in the UV up to the near-infrared regime, the standard method is to have like a non-linear like medium, where the second order of the susceptibility is quite high, so that you can come with a pump photon, like a beam which is pretty intense, and is focused on the material, and then you come with a second like weak pulse, which is called seed. And when the two match in space and time in the material, the result is what is called optical parametric amplification, which is sketched here. Eventually, like you induce a transition by the pump, and like the seed acts as a source for stimulated emission. And the residual photon energy, which is the difference between the pump and the seed photon energy, comes also as a result, and this is called the so-called idler photon. So in the optical parametric amplification, you end up with something like a pump which is never depleted, a signal photon which is amplified, and an idler photon. And I mean, by this you can then consider like the signal and the idler as two like available sources for your experiments. Like if you want to go down in photon energy and, for instance, address the Taylor's regime, then again some kind of frequency mixing is exploited typically. again in solid state, like for instance, zircon telluride is one of the most used material. In this case, this frequency mixing occurs within the pulse. So you come with, sorry, this is very small font size. You come with an ultra-short laser pulse, which can be like some standard 800 nanometer titanium sapphire source, very short, which means also very broad in energy. And the idea is that you can do different frequency mixing within the pulse. So it's an inter-pulse like process where you can match two components of the pulse, do the difference, and this will end up in the Theriot regime. And the resulting pulse will be of the same pulse duration as the incoming one. So you also preserve like really the short pulse duration of the incoming pulse. Eventually, you go in the other direction, the extreme UV range is exploited typically like by means of high harmonic generation in gases. This is actually also quite, I mean, it's not only challenging from an experimental viewpoint, also theoretically there's still a lot of effort. I mean, there are also some talks in the school talking about this mechanism. And the basic idea is that you, after the interaction between like the atomic potential of your gas and a strong field, electromagnetic field, an electron is kicked out of the potential and can tunnel away from the atom. But at a certain point, it will be like accelerated back into the potential and getting energy, which is then released during the recombination. And this energy is in the range of the XUV. So for this part, I refer to this experimental review, but definitely also from a theoretical viewpoint, this is still quite much under investigation. Yep. So it is inside the material, but it's really an interpulse. So you actually need one pulse, which is really very high in the field amplitude, and it's focused onto a crystal. It's in solid state. And the crystal is, again, a nonlinear medium, exactly where you can match like those two components and find the so-called phase matching in between the two crystallographic axes like that enable the different frequency mixing process. Yeah. Okay, so I've shown you that we nowadays can really basically get access to almost any time scale and energy scale with our laser sources, and the Pampos scheme is nowadays also really applied to almost any kind of spectroscopy. Like I would say, the pioneer one was the one by Zivail, transient optical spectroscopy. Time resolved photoemission spectroscopy, like I will show you two type of them, like ALPS and two-photon photoemission spectroscopy are also widely used. But then really, depending on what you want to probe, you can pick up your steady-state spectroscopy and apply a Pampos scheme. Probably the most recent one is really like time-resolved RIX, which is mostly performed at synchrotron radiation sources. But like, for instance, like you see, like Raman spectroscopy and eventually coherent optical phonon spectroscopy are also widely used. And like of this, I will show you an example today. Okay, so let's come to the these three approaches that I was mentioning before, and like get a bit more details on the first one, which is more standard one. If one wants to get access to excited states of the material, you have to go like in a non-equilibrium situation and then apply the Pampos scheme to follow the relaxation dynamics of quasi-particles. So where quasi-particle is also like a really basic concept in time-resolved spectroscopy, being a excitation which is coupled to the environment, and so it's kind of dressed by the environment. For instance, an electron is never really free after the photoexcitation. It can like talk to, for instance, the lattice and like being a kind of a quasi-particle dressed by the phonon, sorry, is coupled to. In a non-equilibrium spectroscopy approach, the idea that the excitation can also involve some actual absorption, but it's still rather weak, that you don't change the landscape potentially in which the system is evolving. And so thereby, ideally, so this is an example taken from superconductors and correlated materials, where upon photoexcitation, you can think of the electron sublattice being heated up rather abruptly, reaching a very high electronic temperature, while the lattice stays kind of frozen at the equilibrium one. And then through coupling with strongly coupled coherent phonons, the electrons can thermalize, reach like a common temperature, and also the lattice is then slowly heating up. And on a much lower time scale, then the energy is eventually transferred to the lattice, and you end up with effective temperature is a little bit higher than the equilibrium one, but nevertheless, like the system has evolved, like as I said, like within the surface potential that it was characterized in the ground state. So, like for this kind of approach, I want to discuss the dynamics in a system, like studied by time-resolved photoemission spectroscopy. And so, I don't know how many of you are like familiar with this matter phase, like an excitonic insulator. It's a theoretically predicted matter phase, which is kind of debated, especially among the experimentalists, whether this is really something that is realized in real materials. And so the basic idea of an excitonic insulator is that you start from a semiconductor or a semi-metal, and if you find that the binding energy of your exciton is actually exceeding the size of your fundamental electronic band gap, like then the exciton formation can potentially occur like without any external stimuli, because it's kind of energetically favorable. And like upon exciton formation, we would end up having exciton which like mixing up a bit like the single particle picture of like an electronic band structure with a true particle picture of an exciton. Like an exciton would lie like kind of energetically below the top of the valence band of a like standard band semiconductor. So as a result, you have like a band gap opens by an amount, let's call it twice delta, where delta is typically taken as like an order parameter for this phase, and it depends on the density of these ground state excitons times their coupling strength. Well, of course, coupling strength I refer to like the weakly screen Coulomb interaction between the electron and the hole in binding an electron-hole pair. Now, in this work, we investigated tantalum nickel selenide, which is a quasi one-dimensional material, by means of photoemission. And in the first place, what you can see is that photoemission can be mostly like performed in true fashion. You've heard a lot about angular resolved photoemission spectroscopy, where you come with a photon which has photon energy larger than the Wolf function of the material, and by that you can directly photoemit from the occupied band structure into the vacuum and get access to basically the valence bands that you can see were like mapped here as a function of energy and momentum. But then you can also like pick up a photon energy which is lower than the Wolf function, and then photoemission will take place only upon coherent absorption of two photons within the same pulse. And this is a trick that is always is kind of quite commonly used now to address the unoccupied states, because of those, I mean, of course, with only one photon would never be addressed, being those bands empty. But with two photons, you can kind of coherently deliver an electron into a conduction band and then photoemit it. And you can see here this intensity appearing like above the electronic band gap of the material and matching the DFT calculation. Now, to address the dynamics of such a material, what you need is a pump pulse. So you basically have a pump pulse again with photon energy below the Wolf function. And the idea is that like with this, you promote electrons into the conduction band, and then you can probe either the kind of leftover population in the valence band or the transiently populated conduction bands. And by kind of recording the intensity at any energy in this momentum resolved map, as a function of pump-up delay, you get, of course, the dynamics of the charges through the bands. This is what we did in this material. And here, so you see that at any energy above and below the Fermi energy, so above and below the electronic band gap, you can record, sorry, the temperature. So here we were in the, let's call it the low temperature phase. The critical temperature for this phase transition in the material is pretty high, 330 Kelvin. And here we were measuring, I think, about 80 Kelvin or so, deep in the low temperature phase, what is supposed to be the excitonic insulator one. So yeah, you can see, so you have basically some initial intensity up in the conduction band, which then is supposed to like cool down, and electrons are collected at the bottom of the conduction band. And this is why like you observe like also energy at the bottom of the conduction band, which collects and relaxes on a much lower time scale. And this was like probed by true photon photoemission spectroscopy. But like complementarily, we were also performing time-resolved like photoemission spectroscopy. I mean, just for the non-expert, I mean, this is really two complementary measurements done in a sequence, like, because of course you have to tune the photon energy and so on and so forth, but like same experimental condition, one after the other. So ideally, like when you can match the time scales and everything in terms of experimental condition, you can complementarily see what's the evolution of the valence band in time. And because you have the energy resolution, I mean, for instance, the conduction band electrons can be followed in their relaxation as a function of energy, and you can see that you that like how to say, like the lower the energy, so the more you move towards the conduction band bottom, the higher the relaxation time, and indeed this intensity is persisting a bit longer than up there. And at the same time, you can tune the power of your pump pulse, so the excitation density, and you can see that also by increasing this parameter, you make the relaxation time like slower. And you can, of course, try to model them, and concerning the energy dependence, you can consider like that at the bottom of the conduction band, you have phase space restrictions for the electrons to relax, whereas, for instance, the fluence is a way the so-called dynamical screening, so the transient screening that the free carriers excited above the electronic band gap like can transiently produce in the system, and the higher the screening, the slower the rate of scattering, and thereby the dynamics gets lower. Okay, so we actually also like as I said, like, look at the valence band, and here something quite curious was happening. Like while the conduction band has fully emptied in the material, there is some residual intensity vacancy in the valence band, which has not recovered. So to say it's seen in a first glance that the number of particles is kind of not conserved in the system, which is pretty odd. And of course, experimentally, one has to verify that you're not just missing in your detected area, that, for instance, being photoemission a surface-sensitive technique, that those electrons are not just too deep into the bulk. So, but once you rule out all those kind of experimental artifacts, let's call it, the question was like, okay, then something really in the physics of this material might happen. And here's where the non-equilibrium spectroscopy approach comes to play a role. And so the idea was that, okay, now let's imagine this material is an excitonic insulator and divide our system into sublattices and develop a rate equation model where you have like the valence band with some unbound electrons, which will always be like present in the system. You have the conduction band, and you have a condensate of ground state excitons, which are present already at the equilibrium. Now, in this rate equation model that we can developed, we thought, okay, we come with a pump pulse, and you promote electrons into the conduction band, both by exciting, like valence band electrons, but also ionizing these ground state excitons, which eventually will end up being like quasi-free carriers in the conduction band. And then if we like expect like a relaxation dynamics taking place first from the conduction band into the valence band, only on a second step, ground state exciton might reform and condense into the condensate, you end up with this set of like rate equations that describe the evolution of the population in each sublattice. And like given that, the photoemission intensity in the valence band might be matched as a composition of the population in the valence band and the population in the condensate, like normalized of the so-called photoemission probability to effectively photoemit an electron from one or the other sublattice. So we use this solution of the rate equation to effectively model our transient like intensity in the valence band, and we could actually reproduce pretty nicely like those transients for any fluence we use, and also we varied a bit like the temperature staying below the critical temperature, and the model was kind of stable. Not only this, once you get basically the evolution of those three sublattices, you could use the first solution to actually map the evolution of the conduction band intensity. So anyway, what you can see here, like this is actually the evolution of the population in the conduction band bottom, and the purple curve is not really a fit to the curve, it's actually the result of this modeling applied to fit actually the valence band. But somehow it was actually, again, able to reproduce the data pretty nicely. So confirming kind of the stability of the model, if you like. So through this like non-equilibrium spectroscopic approach, using rate equation modeling and the evolution of population through the bands, we kind of reproduce both the unoccupied and occupied evolution of the band structure upon photoexcitation, which can be considered as a kind of dynamical spectral frame of an excitonic insulator, in the sense of like probing the effective existence of an excitonic insulating phase in the material, which, believe me, is still quite under debate in this material. And there have been really big effort like trying to find indeed an evidence for such a phase in tantalum omega selenide. So we haven't performed such the modeling, but the thing is actually that there was no vacancy left in the valence band, in that. But we haven't done such a detailed analysis that I can show you actually today. Yep. Mm-hmm. So if you refer to, I mean, of course, when you collect an photoemission intensity, your absolute intensity, of course, is affected by the so-called matrix elements, so how actually sensitive you can be to specific energy region in your band structure. As I said, there are also many other aspects that can prevent you from really count electron one by one. But I would say what you can still follow is the relative energy distribution through the bands, and also along the momentum direction. Yeah. This. I see, but this is why also I'm talking about kind of relative intensity. So, for instance, so you might expect being more or less sensitive to the intensity you are integrating in a certain energy momentum region, but once you follow the dynamics. So in this case, I'm not saying that you have that all those electrons are ending up in this specific energy region at first. What I'm saying is that I see at the beginning a certain time delay between the pump and the probe pulses, some intensity, which eventually goes down to 0. So this is a specific area where you do have some sensitivity. So the matrix element has some weight to the intensity, but then you fix that weight and you follow it the intensity in time. And here, really in this conduction band bottom, which is the very low part here at the bottom of the conduction band, at some point there was no intensity. On the other hand, if you stay here in the valence band, where, by the way, staying at the gamma point, it's really the part where usually this technique is mostly sensitive to, because of energy and momentum conservation and other sets of the measurement. There, what I'm saying is that you have some certain absolute intensity, and if you follow the evolution in time, at the same time delay where the conduction band is emptied, you have still a massive vacancy of valence band. And this is I wouldn't relate it to matrix element if you assume that the matrix element is not time dependent, of course. This is probably the thing. So actually there is coupling to phonons. We have seen it with optical spectroscopy first, being even really selective to excitation at the gamma point. Not only this, by doing this type of outputs, I mean, I'm not showing here the map, but you do see also oscillation, definitely in the intensity, possibly also in the position of the bands that we are probing here in this area. Sorry, I couldn't hear. I'm not saying the phonons are not involved. I would say this, I mean, this rate equation model was probably kind of simplistic, but kind of enough also. In any case, so having electron phonons, typically you use it to, well, see relaxation of the electrons and potentially also like bringing electrons from one case point to another. It wouldn't really probably help in recovering this kind of intensity vacancy. Also because to look at this, to record this intensity, we were really integrating over an area, particularly over an energy area, where you really do include the full bandwidth of your valence band. So if you would, for instance, by electron phonon coupling, like move up and down in energy, for instance, you would stay still within the integration box. And not only that, I mean, this would be like kind of a periodic modulation rather than really a like incoherent recovery of the dynamics. But like, I do agree that in a sense, this approach is, I mean, especially in this way I was showing you, is really almost a toy model. In a sense, was enough to recover the dynamics. And the interesting thing is that once you get these beta and gamma rates, like by tuning the sample temperature, the fluence, we were able also to kind of elaborate a bit more those quantities in terms of like estimate of the energy of this ground state reformation. So what's the energy and the kind of condition you need to have for having such process to occur? Because I mean, the idea is that this gamma is a kind of a compromise in between electrons which are bound to a hole and go back to the condensate, but then, I mean, you're still rather hot, so they also might ionize thermally and go back to the valence band. So it's kind of like a like back and forth parameter. And if this is the end is pointing towards a dominant forward process, then you end up recovering the valence band intensity. Okay, I'm coming now to the second approach, which is well, ideally you can either probe and or actually pump and or probe collective excitations. And the basic idea that if you, for really being selective in the excitation, you typically come with an impulsive excitation. So like, for instance, also no actual absorption is needed. And then the probe pulse like has to record like, the frequency and the lifetime of macroscopic oscillations that are induced in the system. But how this is actually occurring in a time resolved picture, and I mean, I'm gonna show you then later an example, like which, as I said, like was like referring to external phonon dynamics in a semiconductor. So yeah, a little bit more of a preparation kind of description of this mechanism of generation of coherent optical phonons, which is probably the easiest like collective excitation we might think. So it is basically a Raman process. But what it makes different, like the generation of coherent phonons from a standard Raman process, is that usually in a Raman you have like a fully incoherent activation of atoms, which start like to oscillate around their equilibrium position once the pulse is impinging on the material. And then basically, yeah, you come with with a monochromatic wave, a continuous wave. You do a transition, ideally also to a virtual state, and then you have stimulated emission of light, and the frequency difference between the impinging light and the stimulated emitted photons should match the frequency of a lattice vibration. And as a result, you have like Raman scattering light collected and like vibration of the atoms. Now, if you come with a ultra short pulse with a certain bandwidth, you can think of having this Raman process within the bandwidth of the pulse. So again, you have now like this omega 2 and omega 1 being component of your pulse, like, and being then the omega of your phonon, like kind of the difference between them. You can like already like understand that in such a process, like the activation of the atom vibration is kind of coherent because it's within the pulse, within like the interaction with the electric field. And like as a result, a really macroscopic oscillation in your signal is expected to appear. Now, this generation of coherent phonons can be kind of divided into main schemes depending on whether you are actually absorbing or not with your pump pulse. And if you're not in an absorption scheme, so you basically address some virtual state with your pulse, and And then it's really like an effective Raman process where your excited electron ends up in an excited state of your ground state potential, and this results in a polarization oscillation, which is exhibiting a scene-like behavior. So you're really like kicking your mass, but you fix the fixed point of your pendulum, and you see the oscillation around the equilibrium ground state. If you actually absorb, like with your impinging pulse, the idea is the following: you enter an excited state which has a potential whose bottom is kind of shifted from the equilibrium one. In this picture, like the macroscopic polarization ends up oscillating with a cosine-like fashion, and so you can already appreciate that if you have phase resolution on the initial amplitude of your oscillation, you can eventually reveal which is the mechanism of generation of coherent optical photons. Okay, let's see how this applies to the study I was mentioning before. I will discuss this photoinduced modulation of an excitonic resonance in a layer semiconductor, which I will show you how this results from a strong coupling to specific coherent optical phonons. And this study will enable us to discuss about the generation mechanism of those phonons, but also which are the spectral fingerprints of exciton phonon coupling in an optical spectroscopy measurement. And eventually, which are the dynamics that are involved in this material when exciton coupled to phonons. Just few flash material. Smooth-3 iodide is a single crystal which exhibit like van der Waals stacked layers. And the complex part of the dielectric function shows a bright exciton at 2 eV, which is kind of reflected in the reflectance spectrum that is shown here. So you see this sharp feature at 2 eV in the reflectance corresponding to the exciton transition. Concerning the lattice, there is one fully symmetric AG Raman mode, which appears in inelastic Raman scattering, which involve mainly kind of out-of-plane stretching of the bismuth iodine bonds. And in our investigation, we study like the variation of reflectivity as a function of, or as a result of the photo excitation, with the idea is that any variation in the reflectivity corresponds to a photo-induced modulation of the refractive index. And this can be decomposed, oh sorry, I forgot the reference, but this is like from a textbook on coherent phonon spectroscopy in condensed media. So this can be decomposed into an incoherent part, which takes into account the excitation of carriers, and a coherent part which relates to the atomic displacement induced by the pulse. And so you can see, so by basically decomposing your signal into an incoherent and coherent part, that ideally you can probe selectively the charge and the exciton dynamics and the phonon dynamics. The question was like, are those two in a way coupled? Which are the spectral fingerprints of this coupling, if any? Briefly, this is the scheme of our experiment. You come with a laser source which emits at 1 micron, like about 180 femtosecond pulses. And then you split the beam. You get like a pump beam and a probe one. The pump beam is tuned in photon energy in this box, which is an optical parametric amplifier, which is used to tune the photon energy to basically excite above the excitonic resonance of this material. So you are really into the continuum. But not only this, you convert the photon energy and then you deliver your pump pulse on a delay stage, which is used to vary the optical path between the pump and the probe beams. And by that, you vary basically the time delay between the two pulses. And then you focus the pump on your sample. The other beam goes through a process where it is converted into a white light continuum probe, so a very broad pulse. You see here, this is actually one window that we selected out of the probe, which can nicely cover your exciton resonance. And then after this, you focus it on the sample, and what you record is the reflectance out of the material. So our signature is this so-called transient reflectivity, defined really as this difference between the reflectance measured in presence of the pump pulse and in absence of the pump pulse a certain time delay tau, which is set by this delay stage. Normalized over some reference like of reflectance. And for instance, like considering just the excitonic peak that you already record in your equilibrium spectrum, you can expect that upon photoexcitation, several things can happen. Like your equilibrium peak might be quenched, might be broadened due to dephasing and scattering processes, might even shift in energy. When you record such transient reflectivity signal, what you end up having is positive region where the transient reflectivity is increased, or negative region where the reflectivity is transiently quenched, and eventually nodes where the sign of this reflectivity changes. This is what indeed got in this measurement. So you see in this top left map, transient reflectivity as a function of probe wavelength and time delays. And if you slice this map vertically, you can get like transient reflectivity spectra at any delay from the pump arrival. And you, for instance, recall like quenching of the exciton where the transient reflectivity is negative and broadening where the reflectivity is positive. You can slice this map also horizontally and get, for instance, the recovery of the reflectivity signal as a function of probe delay. And here I'm showing the one like resonant to the exciton wavelength. And by fitting this recovery, you get time scales that can be correlated to scattering mechanisms. So here we are back to a kind of this non-equilibrium spectroscopy approach that I discussed before. And like you see, we span from a few hundred femtoseconds up to the nanoseconds, which are the timescales that are required for the reflectivity to get back to the equilibrium one. But on top of this, incoherent part, you do see periodic modulation in the intensity, which are connected to the generation of coherent optical phonons. To confirm that, you can Fourier transform the coherent part. I mean, here is the background subtracted coherent response. You can Fourier transform it and match it with the Raman spectroscopy, and you see the frequency matches. We are indeed also seeing an oscillation in the reflectivity signal at the frequency of the AG Raman mode. But time resolved spectroscopy can go farther because you don't get only the frequency, you can also like really fit those transients with damped cosine function and get amplitude, dephasing time, and initial phase of this oscillation, provided a good resolution of your time zero. And so what you got, for instance, like that this oscillation is damped on about 2 picoseconds, which means that this oscillation vanishes on these time scales. And the oscillation starts with a maximum. So it's like a cosine-like type of oscillation, revealing that the excitation mechanism for this phonon is of displacive type. Okay, we then expand this type of analysis, like Fourier transforming the signal, but also fitting the transients for any wavelength. And here's what you can get, like basically a 2D map of your coherent phonon excitation as a function of like probe wavelengths or probe photon energy. You can see that at any probe wavelengths, you excite only one mode, which is again this AG Raman mode. But the intensity of this excitation definitely varies through the spectral range that we investigated. And if you look at the amplitude of the oscillation, you have some strong enhancement of the amplitude around the excitonic resonance, but also some nodes appearing at a position where the oscillation is shifted by pi's. So you basically have like antiphase oscillation at the left and right side of these nodes. And if you recall the sketch I've shown you before, this points to some shifting of your exciton position over time, for which like the effectivity is changing in sign and exhibits some nodes. Now we wanted to confirm that because this would actually point to the fact that like we have strongly enhanced oscillation at the excitonic resonance, probably due to coupling between the exciton and the phonon. And to do this, I mean, we collaborated with Davide, Alejandro, and Simona, performing DFT with like beta salpeter approaches that enable us to also study excitons, and this you know way better than me. So this is what they did, and so basically starting from the equilibrium spectrum of the system. Here's the complex part of the dielectric function. They found that the excitons in this material are pretty localized, basically within the first the first layer and a little bit on the one next to the main one. The exciton binding energy is particularly high, on the order of like 300 millieV, which is really, really a high value for a like bulk semiconductor. Then, I mean, having this information at equilibrium, what they did was to really displace the atoms along the vectors of the AG-Raman mode, and we calculate with solving the beta-Sapieto equation the dielectric function. You can already see that by shifting to the left or to the right, your atoms, the excitonic peak at equilibrium exhibit, actually not at equilibrium, but with the displaced lattice, exhibit some shifting in energy. So, of course, having the dielectric function, you can get the reflectance with this displaced lattice. And from that, what they calculated is the so-called reflectivity variation, which can be then compared to our transient reflectivity, or at least the coherent part of our transient reflectivity. The way it is defined is indeed like the difference between the reflectance with the atoms being displaced from the equilibrium minus the reflectivity at equilibrium or normalized over the equilibrium ones. And this is depending on the direction of the atomic displacement, this type of reflectivity variation spectrum that you get, where you see parts which are like positive or negative, and some nodes with the sign of the reflectivity variation changes. Okay, we took the absolute modulus and the sign of this quantity and compare it to the initial amplitude and the phase of our experimental data. Here is the result. So you can see nice agreement between the evolution of the phonon amplitude over probe wavelengths between the experiment and the calculation, which also reproduce both the enhancement and the nodes at the expected position over the probe wavelength range. And so in this way, we could kind of establish this amplitude enhancement and pi phase shift of the oscillation phase being the spectral fingerprints of exciton phonon coupling. Because I mean, theory could tell us like really what's the origin of these experimental signatures. And in a sense, this was also closing the gap between experiment and theory, because I mean there were already quite some effort in the past trying to reproduce all the spectral fingerprints that theory predicted, but somehow were not like fully resolved in previous like works. Now, having this spectral fingerprints kind of determined, we wanted to look at the dynamics. I mean, we have time resolution. So what we did is having this prediction from DFT in mind, we followed the position of the excitonic peak at any pump-up delay. So here you see one exemplary like differential spectrum and the fit of this. And basically, we were really monitoring the position of this bleaching, which should correspond to the shifting of the oscillation. Oh, sorry, shifting of the resonance. We observe like a rapid redshift, which we attributed to the fact that we are indeed absorbing into the continuum, so the dynamical screening is probably activated. And then on top of this, the peak is found to modulate at the frequency of the phonon with a damping time, which is corresponding to the dephasing of the phonon oscillation. And so this modulation up and down is then later connected to the displacement of the atoms on the left-hand side and right-hand side with respect to the equilibrium position. This correspondence enables us to do one step forward. So from time to energy domain, we can now think of feeding this value got from the experiment into the calculation, and basically ask ourselves which are the required displacement to get such an like modulation in the excitonic resonance. So basically, we move from energy to real space domain and track, like by calculation, the atomic displacement that corresponds to the effective peak shifting which is measured. Of course, a peak shifting which can be then experimentally tuned by varying photon energy, and especially like the pump power or excitation density. So ideally, like having a way to eventually control also like the evolution of the excitonic resonance fully optically. Okay, with this, I mean, those are the two main results of this other talk. I probably just flash very briefly, really, give you just an overview of works towards optical control. I'm just really listing them because it's probably the newest topic, but also the more complex and widespread one. You can think of the first pioneer work in the field of transient superconductivity as a way to selectively pump phonons, and by that, like, get access to coherent oscillation of the lattice that can induce some kind of metallicity in high Tc2 superconductors being in the low temperature phase. You can think of having bandgap control of an excitonic insulator by means of light, or even more recently, there were evidence of non-equilibrium charge density wave order, which were studied in terms of ARPES. For even like more really broad overview of what's going on in the field of optical control, you can refer to this literature, where really by spanning the strength of the electron correlation and the strength of like interaction between electrons and the lattice, and the photons, like really this wide area of this phase diagram can be explored. I'm really at the end of my talk. Perspectives. I've talked a lot about exciton dynamics, and stay in this field. There is now a big effort, which was promoted by theory, actually, in trying to address which is the signature of an exciton. Not only an excitonic insulator, actually even one step behind, like in a single exciton frame. And after this work by Kemper and its group, where the idea is that somehow the photoemission signature of exciton should have some memory of the holes which the electron is bound to. Well, there is now quite a decent number of works by terms of photoemission, which you can refer to, where they were really trying to get this signature out of the spectrum, disentangling that from the signature of the upper conduction band, for instance. And I think, with this, I would like to conclude, because there is another topic which I'm probably just flashing the reference to, addressing coherence. Addressing coherence is also really hard because it's very fast, and because it's not also obvious to get a spectral fingerprints for that. For this, like multidimensional spectroscopy, both in the optical and spectroscopic and photoemission frame, are currently in development, I would say. But with that, I would like actually to come to my acknowledgement of the main players of the two works I was talking about, which are all listed here. And I thank you for your attention.
So thank you, Selene, very much. So she gave us an overview of what can be done experimentally, also discussing in specific two experiments. We already had a bit of discussion during the talk, but so if you have any other question. Okay, so yeah, maybe since we are late, if there are no other questions, we move to the next speaker, and we thank Selene again.